Hi, my name is Kevin Hoffman and I'm a sophomore student at Ursinus College. I'm excited to share with you today the research applying theoretical methodology known as LP linear regression using simulation. In this project, we confront the problems surrounding non-normal probability distributions of the error term when performing linear regression and how we can best accommodate these settings. Simple ordinary least squares, or OLS regression, finds a model to describe data by choosing regression coefficients, i.e. the slope and intercept, to construct a line over the data. These coefficients are calculated by minimizing the sum of the squared errors, thus making OLS an L2 function. There's an inherent consequence when minimizing this way because outliers are disproportionately weighted relative to data points that are closer to the central tendency. In other words, as a point's distance from the line increases, the influence that it exerts over the coefficients increases nonlinearly. Abnormal presence of outliers may accentuate this disproportional effect by pulling the coefficients away from the true parameters. One study worked with theoretical proofs of choosing the power that the error term is minimized over to limit the influence that outliers exert on the model. Questa matran chi this LP regression. LP regression varies from OLS regression by minimizing the error term sum to the pth power rather than the errors squared. By choosing p, we are affecting the sensitivity of regression coefficients to outliers. It is important to note that when p equals 2, LP regression functions indistinguishably from OLS regression. Thus, changing p from 2 would affect the influence that outliers exert over the coefficients in the minimization problem. Since raising p will disproportionately increase the weights of outliers, it increases regression coefficient sensitivity to outliers. Meanwhile, lowering it would diminish the weight of outliers over selecting coefficients. When outliers occur more frequently, lowering p should provide more accurate regression coefficients because those outliers would have less influence over the model. Theoretically, we should also see this for raising p when outliers are abnormally rare. Calculating the LP regression model initially proved difficult because fundamental equations to solve the first-order conditions for optimization in OLS were no longer an option because the LP regression equations are derived from functions outside of the L2 space. As a result, we used Newton-Raphson numerical optimization methods to solve for our LP regression coefficients. This method is an iterable approach, finding an approximation of the root, allowing us to converge onto our regression coefficients. Thanks to R&R Studio, we simulated lots of data in 4 sets of classes where each class exhibited errors with a normal, Cauchy, uniform, and exponential probability distribution, respectively. We then fit in OLS and multiple LP regression models over the data, with p's ranging above and below 2. After many repetitions, we compared the regression coefficients of the OLS and LP regression models by using the mean squared errors, or MSEs, of the regression coefficients to the simulated data's actual parameters using standard t-tests. Our test on the difference between OLS and LP regression coefficients is shown by the figure on the right, where we compare the p-value of the t-test to the parameter p of the LP regression models. That is, what is the significance of the difference in coefficients between the models and across error term distribution? From this plot, we simply observe that a sufficient change in p causes significantly different coefficients between OLS and LP regression models. The key takeaway here is that across error term distributions, there are cases in which LP regression and OLS perform differently. Our next figure shows which model's coefficients were better on average. Since the t-statistic of the test was based on the MSE of the OLS coefficients minus the MSE of the LP regression coefficients, a positive sign indicates LP regression superiority, while a negative sign indicates OLS regression superiority, because MSE is inversely related to model performance. For normally distributed error terms, the t-statistic was always negative, except for when p equaled 2, meaning that OLS performed best under normally distributed errors, and as expected, the two models performed identically when p equaled 2. This latter statement was true regardless of the error term distribution. For models with Cauchy and exponentially distributed errors, the t-statistic was positive for p's less than 2, meaning that LP regression performed better than OLS, and negative for p's greater than 2, meaning that OLS performed better than LP regression. Intuitively, this makes sense because the exponential and Cauchy distributions exhibit heavy tails, meaning increased likelihood of outliers and beneficial for lower p's. We saw the opposite results when the error term was uniformly distributed, such that LP regression performed better than OLS when p was greater than 2 and worse when p was less than 2. This is what we expected because lowering p is good for modeling in the presence of outliers, so raising p must be beneficial for lack of outliers. We can make some key conclusions from these results. we have evidence to make the claims that LP regression is identical to OLS when p equals 2, which is the optimal p for normally distributed errors. LP regression can produce different coefficients than OLS, and that LP estimators can be better at modeling data. Specifically, it is better when the error terms distribution exhibits heavier tails and p is greater than 2, and in the opposite case when the error terms distribution exhibits lighter tails and p is less than 2, because p is a weighting factor of errors. Generally, this study shows how simulation can be used to attack theoretical and complex problems. Further studies regarding real-world application and theoretical next steps would be beneficial for the community to better understand the model. One that I personally find most interesting is finding an optimal p where the model would perform best. Here are the papers that I referenced when undergoing this research. I would like to thank my advisor, Professor Montesinos, the authors of these papers, and the EUSR for this platform allowing other undergraduates and I to convey the hard work that we all put in. Thank you for your time.